Hello everyone. Today I am going to show you a software. Hello everyone. Today I am going to show you a software. And you see how the software works. For teaching online, we use this type of software. You see, these are the these we use, and the name of this software is very useful software. This is Note 3, and use this for teaching online. And today we are going to start a new chapter, that is work, energy and power, and see what are the various things given in work, energy and power. Today we will learn a few terms. After that we will have a different thing. What is the meaning of first? We will learn about what is the meaning of power. Actually, power, work, energy and power. What is work? That I am going to define. First of all, work, power and energy. Work, energy and power. This is chapter number 5 of NCERT. Work, energy and power. First of all, you know what to first we know the definition of work. Actually, if we found the work, that is, work can be written in this way, that work is equal to F dot S, where F is called known as the force. F is known as the force, and S is known as the displacement. So in very short, you can say that work is whenever there is a product of force and displacement. But remember that since this is a dot product of force and displacement, work is a scalar quantity. You remember this one, that work is a scalar quantity, because work is a scalar quantity because the product of force and displacement is scalar quantity. And you know that F dot S can be written as modulus of S into cos theta. This is the work done. So can be written as work is equal to work is equal to modulus of S into cos theta. And this theta can be the angle between force, where theta is the angle. Theta is the angle between force and displacement, So it is very clear that if there is we can find the work in this way, that modulus of F into modulus of S into cos theta, and theta is the angle between the two, right? So this is scalar product. So is scalar product or dot product. We say it as scalar or dot product. Scalar or dot product of force and displacement. Scalar or dot product. Whenever there is dot product, the resultant is always scalar quantity. So we say that work is a scalar quantity, right? Now we'll learn about, this is the definition of work in the case of science or physics. These are, so we find this is a work is a scalar quantity, and we find in this way that A dot B equal to AB modulus of B into cos theta. And if we find the notions of work and kinetic energy, the work energy theorem. Now we are, this is the definition. Now in which case work is 0? Number 2, conditions for work to be 0. Condition for work to be 0. What are the conditions so that the work can be 0? There are 3 conditions. Number one is if force is 0, then work will also be 0, right? Work will also be 0. Number 2 condition, this is the second condition, if displacement is 0, displacement S is 0, then work done will also be 0. And our third condition is that if theta is equal to 90 degree, it is in that case also work done equal to 0. Why? Because we know that value of cos 90 is equal to 0. So in these three cases we got the value of work to be 0. If f equal to 0, if a equal to 0 or theta equal to 90 degree, then we get the value of work as 0. Now we will go to the another theorem, that is the work energy theorem. Right? Now we go to work energy theorem, or notions of work and kinetic energy. Notions of work, notions of work and kinetic energy, of work and kinetic energy, and kinetic energy, and kinetic energy, kinetic notions of work and kinetic energy, and kinetic energy. And this is what we call it as work energy theorem. This is known as the work energy theorem, the work energy theorem, the work energy theorem, energy, the work energy theorem. The work energy theorem, this is known as work energy theorem. So we'll found two or important things so that you can find work energy theorem. The following relation for rectilinear motion and constant acceleration has been encountered in. So we know that. So we are finding the work energy theorem. We know that there is a formula that the following relation, the following relation for rectilinear motion, rectilinear motion under constant the following relation for rectilinear motion under constant acceleration will be, we know this one, that v square minus u square is equal to 2a into s, right? And this can be written as, right? So it can be written as this one, or, right? So this is equation 1, right? And if you multiply both sides by half m, multiplying both sides by half m, we get, what are we getting? You see here, we are getting half mv square minus half m u square is equal to half m into 2 into a into s, right? So these two will cancel, and we are getting ma is equal to, that is ma into s. So we are getting that half mv square minus half m e square is equal to, m is force, that is force into displacement, and force into displacement is written as work, right? Right? If S, the relation follows Newton's second law. We can generalize this equation. We can generalize. We can generalize to 3 dimensions. Generalize to 3 dimension. 3 dimension. Generalize to 3 dimension by employing vectors. By employing vectors. By employing vectors. So you can write generalize this equation 1. B square minus C square is written as B square minus C square is equal to 2 A dot acceleration dot D is the displacement. We generalize to 3 dimensional vector where A and D are acceleration and displacement vectors right. Now if we multiply both sides, now if you multiply both sides by half m, we are getting half m d square minus half m u square is equal to half m into 2a dot d, and these two will cancel and we are getting m a dot d vector, or we are getting m dot a is f dot d. So f dot d is work, right? This is work. So we get this result actually. So what we get? We are getting this one, that is half m square minus half m square equal to this one, that is f d or work, and half m square minus half m square is equal to f d or work. This equation we got. So the above equation provides a motivation for the definition of work and kinetic energy. Now you see here, this half m square minus half m square equals change in kinetic energy, and this w is the work done. So we can say here as that the above equation provides a motivation for the definition of work and kinetic energy. That is, change in kinetic energy is equal to work done, right? That means you can write it is half m b square minus half m e square is equal to work done. Or you can write here in another way, there is kinetic energy, the kinetic energy final minus kinetic energy initial, that is going to do the work done. This is the work energy theorem. The change in kinetic energy is equal to work done. This is what we know as work energy theorem, right? So where K final and K initial are respectively the initial and final kinetic energies of the object. Work refers to the force and displacement. Work refers to the force refers to the force and displacement, force and displacement, force and displacement. What is over which it acts, right? So work is done by force on the body over a certain displacement. So you can define that work is done by a force. Work is done by a force on the body over a certain displacement, over a certain displacement. So what we get, the change in kinetic energy of a particle is equal to the work done on it by the net force. So in the result is that the change in kinetic energy of a particle, the change in kinetic energy, the change in kinetic energy of a particle, the change in kinetic energy of a particle, the change in kinetic energy of a particle is equal to the work done on it by the net force. This is what we call it as work energy theorem. That means work energy theorem is kinetic energy final minus kinetic energy initial or change in kinetic energy, that is equal to work done. This is the work energy theorem or kinetic energy theorem. This is what we call it as. This is called as work energy theorem. This relation is known as work energy theorem. This is known as work energy theorem. So we find this and we get this for constant force, right? So this is work energy theorem. So we have got the work energy theorem is this one, that work energy theorem. We got the work energy theorem. So this is what we call the work energy theorem, right? That is, change in kinetic energy is to the work done, or change in kinetic energy of a particle is equal to work done on it by the net force. So we got the definition, and we come across another thing that is about work energy theorem, and that is the change in kinetic energy is equal to the work done. And now we find another thing, that is work done by force is defined. What is the definition of work? The work done by the force is defined to the product of the component of the force in the direction of the displacement and the magnitude of this displacement, right? This is, I already told you, that is W equal to F dot T modulus of A modulus of T into cos theta. That is the work done, right? So there are three cases no work is done. First one is if the displacement is 0, work done will be 0. If the force is 0, work done is 0. And if the angle between the force and displacement is 90 degree, even then the work done is 0. These are the three types of work done. In the next section, we will discuss about positive work and negative work. Thank you everybody for watching this video.